an interpreter mode for Triton code is to allow users to apply print, like Python's native print, or attaching a debugger to step through the execution of individual Triton programs. Think about if you have hundreds of GPU programs running in a single Triton kernel, using the interpreter will go step through each program individually in sequence and allows you to inspect the data and computation of each Triton program. And it was mostly designed for front-end users. It could also help compiler developers to get the expected outputs without writing a corresponding PyTorch or Pallas program. The related files are mostly under interpreter.py. There are also some atomic intrinsics and also some load and store intrinsics in src interpreter.cc, and related tests are currently using the same test files in unit language, and all the tests that support interpreter are marked with pytest.mark.interpreter. So let's revisit Triton's front end. So given a Triton program written in Python, we will first take into the code generator, which will visit the Triton program as if it's going to visit a standard Python AST. In this AST visit process, we'll go through some JIT functions at first, which are decorated with Triton.jit. Those JIT functions could be arbitrary functions from Triton standard library like run.py or standard.py or custom Triton functions you define. Those JIT functions will call built-in functions internally, which are functions like tl.arange or tl.load. Those functions exist in files like math.py, core.py, or libdevice, which is the third-party library provided by NVIDIA. And underlying those files involve semantic.py, which actually emits the IRs. It calls the IR builder, which first emits Triton IR, then go through, as you know, go through the backend compiler transformation, including Triton IR to Triton GPU IR, Triton GPU IR to LVM IR. Then finally emits IRs on each vendor's GPUs and also binaries. Then here's the difference between the traditional mode and the interpreter mode. We are still given Triton Python programs, but instead of going through the code generator, now we're going to feed this input into the interpreter, which executes those JIT functions in the eager mode. Instead of generating IRs, it will still visit the JIT function with the same pipeline as before, like going through the standard.py built-in function and underlying semantic.py. But then we intercept the IR builder and replace it with interpreter builder, which emits NumPy functions or NumPy data structures instead of emitting Triton IRs. So this is a major difference. There are some exceptions in emitting code for something like tl.reduce and tl.scan. They are not lowered through the interpreter builder because the make combine region function, which used by semantic.py invokes the code generator. But in the interpreter mode, we cannot use the code generator, so we directly replace tl.reduce and tl.scan with custom implementations. For native ops like numpy.sum, they are accelerated through numpy, but if you define your combined functions yourself, they might be slow, but it's still supported in the interpreter mode. Other functions and classes that can also do not go through the interpreter builder like tl.range, tl.range, tl.static assert, and static print. We also replace them with some custom Python implementations. So here's the bottom line for how you can use the interpreter. For now, the only way to enable the interpreter is to supply environment variable Triton interpret equals 1, then append your original command for executing the application. Then every Triton kernel you invoke through Triton's default decorator will be done in the interpreter mode instead of the JIT mode, in code generator mode. You can also attach PDB to debug your program, you first prepend Triton interpret equals 1, and then plus PDB. For example, the file you want to debug is test.py. Then after you launch PDB, you just set a breakpoint at something like test.py line number like 1, then running it through as if you are debugging a normal Python program. There are some highlights. For example, you can set device equals CPU to execute with interpreter on your laptop without actually having it running on the GPU. You can also print values stored in tl.tensor using native Python print and check all values. Here's the ecosystem we built based on the interpreter. Underlying component is, of course, the core Triton part. And above it, we have the code generator mode and interpreter mode. You can view the code generator mode as the lazy execution in deep learning frameworks, and the interpreter mode as eager execution, which is better for debugging. Then built upon it, we have a third-party library called Triton Visualization, which allows you to inspect tensor access regions using a visualizer that you can toggle the bars to switch between programs. And above it, we built a set of tutorials called Triton Puzzle, which are probably good materials for Triton starters to begin with and get to know more about Triton. So here's the coverage of our Triton ops to date. So as far as I have checked manually, all the ops in Triton's documentation have been supported except for inline assembly. The plan for assembly is probably let users specify the semantic of inline assembly using NumPy operations so that we can replace it with those specifications. Otherwise, I don't see any ways to support it for now. There are, of course, some limitations to the interpreter mode, but all of them probably could have workaround. First, if you declare a scalar, there's no implicit conversion from a scalar to a tensor. So, for example, if in the original Triton mode you have a equal 3, then you want to print a dot d type. In the interpreter mode, it's going to throw a runtime error. Instead, you can wrap around a equals 3 with tl.4 or tl.2 tensor. There's another thing which is probably difficult to support, which is indirect memory access. For example, if you want to load a tensor and use the value loaded as the pointer that is going to be used in the next load, it's not supported at this moment. Some precisions are still not supported, like bfloat 16 and bfloat 8 series, but float 16 is already supported. Also, for now, you can only interpret all kernels because you set up environment variable, and we think it's probably difficult or dangerous to change this environment variable at runtime. And since we intercept all the Triton function calls, if you do want to support selective interpretation, like interpret one kernel but not the others, letting others running on the GPU still, we need to use import lib.reload TL to reload all the original functions. And each function is executed in a fixed order. We first execute the first program, which is like first CUDA block, then the second, then the third. They are not going to execute it in a random order, like as if you are executing on the GPU. The overhead might be high, especially for TL.reduce and TL.scan with custom associative operators. The visualization library kind of mitigate the problem by sampling programs. There are several action items we are currently working on. First, we want to add a documentation page in Triton's website, and we want to figure out some ways to reduce overhead. Probably we want to support selective kernel interpretation, like only interpret some kernels, but not all. And currently, Torch Inductor doesn't support this mode yet because they use their own launcher to launch Triton kernels. And if you do think the interpreter mode helps in your cases, please feel free to apply it in your applications for correctness or performance studies. That's it for today's progress update. Any questions is welcome.
How would you choose a kernel? Would you consider adding an annotation like the Triton JIT to say, I don't know, Triton interpreter on the kernel to indicate that that's the kernel that you want to interpret?
Yeah, this is how you enable it. So for now, we just enable the environment variable, but if you do want to support selective interpretation, we think you can either add a decorator on top of triton.jit or applying a function like triton.trace or triton.interpret something and use the function name as the parameter passed into the like interpret function.
Okay.
Yeah, that's just my personal proposal. It's not there yet.
Is there any way to fast forward the program blocks? Say if I'm debugging, iterating through program block 1 and I want to fast forward to program 32, is there a way to do that?
Well, you still need to execute all the previous programs, right? We cannot like offload some of the programs in a
It's just
kernel
that
on
I'm
GPU.
wondering if there's a way that we can do this fast forward.
For now, no, but that's a good point. Yeah.
I think what I would do is probably just hard code the variable of the program IDs to be the program ID that you want. It's not great, but that would then the first program would execute with the program IDs you want.
Wouldn't you be able to put like a conditional breakpoint or something like that? Would that not work?
Yeah, you can also do that.
Yeah, but all the stuff is still executed on CPU, so it will still be slow.
Okay, thanks.
Okay, thanks, Karen. Next, there was Intel. The Intel team wanted to have a discussion about TMA support. So, Ettore, do you want to go ahead?
Yeah, no, I was just curious. So the TMA support is being removed. It was more of a curiosity. I had actually a couple of questions. One is it going to be removed for good? What was the experience with TMA? And so, in general, your experience with that feature and whether it's going to be replaced by something else or is gone for now. And the second question was about the block pointers. We want to know if block pointers are going to be continue to be supported or there is any plan to drop support for block pointer, because we saw a tutorial being removed. It was testing block pointers. So I don't know if that was a mistake or and it can be put back, or it's more like the block pointer will eventually be removed at some point.
Yeah, I can talk a bit about that. Thomas can give more details on our specific TMA plans because we do have some. The long story short is we were really not happy with the way they were implemented initially for the initial Hopper support, and that added a lot of technical debt, and they were not usable in a lot of cases for us. Internally, they crashed when you try to use them. And so our plan, what we decided to do was we're going to remove them for now, and then we're going to think hard about how to do this again better, so we can have TMA support again for the next generation of NVIDIA GPUs. So that's our current plan right now. We still want, to the extent that's possible, to support TMAs implicitly. So the one tricky bit about that makes TMAs hard to support in Triton is the fact that the descriptors have to live in HBM memory, and Triton does not manage HBM memory. I know unlike other hardware vendors that they might live in SRAM, and that can make things simpler. But supporting TMAs in a way, like block pointers efficiently in a way that's portable and sort of like works for both HBM descriptors and SRAM descriptors is a little bit challenging. So we want to take our time and figure out how to do this well. We don't really have plans to remove the block pointer abstractions, like at least the thing that it tries to expose, which is structured memory access, is something that we want to keep. The API might change a little as we want to add things like, I don't know, like other ways to represent different kind of structured memory access that may not be like 2D dense blocks.
Okay. So you're thinking more of an extension, like make it more generic.
Yeah, I think we might try to make it more generic at some point. But yeah, we removed the tutorial because I think it crashed the documentation and now it's just like syntactic trigger effectively for the NVIDIA backend. And I think also for the AMD backend. So yeah, we removed it just so we didn't have to maintain the tutorial. But there's no plan to get rid of structured memory accesses.
Yeah. Oh, that's good. Thanks.
Okay. Next, we have Ian for the CGO trip report.
Okay. I prepared a couple of slides. I'm gonna open up a discussion. Maybe folks have questions, but let me see. I'll get this set up. So CGO, the big compiler conference, was in Edinburgh earlier a few weeks ago in March. I attended the conference and I was at the compiler for machine learning workshop. So there was a lot of discussion about Triton. I gave a talk about Triton, so I got a lot of questions from folks about the language, about the community, about the direction things were going. So I was going to share a little bit about those discussions. Folks are unfamiliar with CGO or need pointers. I got links here. I'll share the slides after the after this meetup. One goes to the CGO main landing page, and the other one to the compilers for machine learning landing page. The compilers for machine learning was probably the thing that was most relevant to this this group. There was a number of talks that were tangentially related to Triton, and then these three talks were sort of more directly related. So I gave a talk about the Triton shared project and how it links to Triton, and Javad gave a talk about his experience at Qualcomm supporting their hardware using Triton. And the two of us answered a lot of questions that folks there had. There was probably about 40 people or so at the workshop, which was it was, you know, we packed the room. It was really really interesting, very lively discussion. And then the other talk I listed here was actually not about Triton, but it was about another project language I think was called Turbine that is very similar to Triton, which is sort of trying to do a kernel language on top of IRI. So there was some questions and discussion about what the difference is between Turbine and Triton and whether they could be combined into a single sort of approach. We got a lot of questions. The most common question was about PyTorch. So like, how is PyTorch using Triton? What is the plans for that going forward? How does that work? And that fortunately, that's something I know very little about, so I wasn't able to answer a lot of questions there. So I know there's probably a few folks here from Meta and folks from OpenAI. We might want to think about how to make that more visible, sort of like a place for folks to learn about what the connection there is and what the plans are there. Because I think it's maybe visible to the community for those who are on the inside, but from the outside looking in, maybe it's not quite clear what the thinking there is, especially around multiple platforms and long-term what the thinking is. There was some questions about like that ties into the other group of questions we got, which is about performance compatibility. So what's the thinking in the Triton community around moving kernels between GPUs and moving kernels between GPUs and non-GPUs, that sort of stuff. And then there was a few people that had codegen bugs with Triton shared. And so I just want to reiterate the same thing which I mentioned to them, which is that if you're hitting issues using the conversion passes that are in Triton shared, please post on the community or raise the issues up so we can address them, because those people are like, oh yeah, I never actually opened a bug. So that's always really good, at any project. And then the last point I was going to touch on, Goshen Kester runs some kind of computational chemistry lab, and she was looking at Triton for HPC, and she has a paper coming out soon, she mentioned. So it's kind of interesting for using Triton for non-ML topics. I don't know how interesting that is to the community, but I guess she had good results compiling her code through Triton and good performance. Yeah, I don't know. The slides from the talks for myself and Javad are available. Kunwar's talk doesn't have slides yet, but I should show up soon. Folks curious what we talked about more detail. Any questions? Anything folks want to super interested in, want me to talk about? No. It was good. It was good to see the community's interest in Triton. I think folks are really hungry for something that is easy to program in, cross-platform. A lot of the things that Triton is shaping up to be. So that's good.
Yep. Thanks, Ian. Thanks for the trip report. Yeah. Okay. So moving on, is the AMD team here? They wanted to give an update on the upstream CI and unit tests status. Yeah. Go ahead. Yes.
Let me share my screen. There's my screen. Okay, so I'll give
yes.
I'll just have one slide. So I'll give a very brief update about our upstream progress. So for now we have a CI machine which is MI 210, and this is we're using a ROCm 6 Docker image to run the CI. And for now we are focusing on the test core.py, and we have one test left, that is test.3d, and we just need some refactors. The functionality is there. And another thing is that this is for the CS for MI 210, and we have some test that is failing on MI 300, so we are working on that. So test full and test atomic CAS, those are failing on MI 300. We are working on that. And for some plans in the future, we are going to add MI 300X CI so that we can make sure that we will not have regressions on MI 300 performance-wise and functionality-wise. And we are also enabling tests in other files other than test.core.py. This is functionality-wise. Another thing is about performance gap between our fork and upstream. So for now, this is just an FP8 gen performance. So I just want to give you guys an impression about the difference. So in the fork, we can get something like 1,100 TFLOPS, but in upstream we can only get less than 1,000 TFLOPS. The reason is the reason is that we don't have this fix for now. So there are some shared memory allocation paths. We need to fix that because we are using a stream pipeline path, which is slightly different from the pipeline paths that are used in upstream. So we need to fix the alias related stuff so that the allocation paths will not think that we need that much shared memory LDS. And another thing is about the LDS vector size. We need to enable a larger vector size to boost up the performance. Yeah, I think plan-wise, I think we can try to upstream these two PRs this week so that we can get the perf on par sometime this week. And for flash attention related kernels, we are fixing some compilation errors, and after that we can bring up the perf. Yeah, that's it. Any questions?
Yeah, thanks, Li-Xun. I also want to chime in that thanks for the community support. And I think we are making pretty good progress on AMD GPU backend. The next stepstone for us is to completely move the development from our local repository to upstream Triton in the coming weeks. And we are also getting all the dependency project like PyTorch to move to Triton upstream as well in the coming weeks. And also we are working with the team to plan for the next release on the AMD side of supporting parts.
Yeah, thanks, Pang and Lishun. Are there any questions for the AMD team? Okay, so next we have open discussion. Are there any topics anyone wants to cover? Yeah, go ahead, Alexander.
Hello. Yeah, I have a question in regard of performance test for the GPU part of the Triton. I especially mean the launcher, the kernel launcher. So we use a pretty old version of Triton that is maybe half a year old, and recently I tried to upgrade it to the most recent one, and I noticed that in my test the kernel launch started to kind of twice time as before. Yeah, I wonder actually, yeah, so I guess that a lot of effort is spent on making the GPU code works as fast as possible, but what about the CPU part?
Yeah, I can take that. And by the way, I have to leave after answering that question because I have another meeting.
Thank you.
Yeah, so I think when it comes to overhead from launching kernel, we're kind of fighting an uphill battle against Python. And most of the things we did before to try to make the code more maintainable also ended up increasing the overhead of launching kernel. In practice, we haven't like invested a massive amount of effort in trying to find something that helps both, because internally at OpenAI we don't really care about launch overhead due to our setup and how we like use Triton. And I think PyTorch also hasn't run into this issue because they use like Triton.compile, and I think in general the recommended way to like use Triton most efficiently is either with CUDA graphs or with Triton.compile. That said, we're aware of the issue. I think that there was a pull request that aimed at improving this that was submitted like last week. Right now, we don't have time to review it, unfortunately, because I think it would require like extensive review and extensive internal testing in our infra to make sure that the replacement wouldn't break our system setup. Yeah, so I guess that's the answer I can give. Is in general, it's preferred to use Triton.compile or CUDA graph tracing, but at the same time, we're aware of the problem, and when we have time, we'll review that PR submitted.
Thank you.
And I need to drop, so thank you and see you.
Thanks, Phil. Yeah, Whitney, go ahead.
Yeah, I have a question about the refactoring of like putting target like backend dependent code to the third-party folder. So I see that for the Triton GPU to LLVM convert pass is already a lot of it is moved to the third-party backend folder, and they have common utility, and some passes, if you can have common code, is used the common code as well. That is awesome. But we encounter some problem is some of the utility function uses the layout that is specific to backend, like the MMA layout for NVIDIA or the WMMA for AMD and so on. But since the Intel code haven't landed in the community code, so our DPass layout is not there. So we will end up have to duplicate the whole pass in our third-party Intel folder in our fork. And I wonder if there is more active work of refactoring those utility as well to be more backend friendly. And other one is the dialect. So there is like still some backend related dialect in the common area, like the NVGPU or the Triton NVIDIA GPU dialect. So is there also plan on moving those to the backend, the third party folder?
Yeah, I can take those questions.
Thanks.
So yeah, I have multiple questions, but to start from the beginning. So about the layouts, there are multiple things that are kind of planned, but not necessarily super short term. So one thing is like people are welcome to add more interfaces if that helps your case on Intel size. Definitely, that's something in the past we've accepted, and it helps the code. It helps everybody in general. If you feel like your cases can be handled by just adding one more abstract, like one more interface, or adding to the existing interfaces for layouts, that's great. We do have a longer term plan to try to unify all the layout representations. Yeah, it's still a bit of a vague plan, and we don't have the design fully baked out, but that's something we do want to address on the long term. Like there were discussion about, like I know NVIDIA suggested using Qt layout, which we don't necessarily think it's ideal, but something like that where we could unify all the layout, something we would want, but it's not going to happen right away. It's going to take time to get there.
Just
and for the, I guess, yeah, go ahead.
No, sorry, just so thanks, like, yes, it's good that if we want to add an attribute, we can, but I was thinking for the utility portion, the portion that is in the common structure of the code, would it be okay to split it so that we can move the backend specific part of the utility inside the third-party directory for that particular backend, so that utility in the common code are really just common stuff.
That's fair. If a utility is clearly specific to a backend, it should move into.
So if in this case there was something that was specific to a layout that is for NVIDIA or so that part is split. Yes, I mean it may be more complicated than to disentangle the whole thing, like, but if we have a pull request, then we can probably submit a pull request and go through code review.
Definitely. Yeah, feel free to send a pull request. We have tried, and Zahi has done a lot of cleanup in this area of like trying to untangle things. Some, like most of what is left is the non-obvious case where there is a use of maybe a layout or something that is backend specific, but it's way deep into some logic.
Right.
And that
like we can find it because we're not in tree, and if you're in tree, you're not going to find this very easily. So we can in that case, because we're not in tree, we have a slight advantage, and we can expose some of these, fix.
I think, yeah, those fix
and help fix it. Okay, thanks,
Tom. You're welcome to send PR there, and yeah, if it improves the layering, that's definitely an advantage for everybody.
Thank you. And then the other question about the dialect, what's the response to?
I mean, I think it's the same response, right?
Okay.
Like, yes, we do have some cases where there's still dependency. It's mostly because, yeah, it's not like an obvious, it's not a super trivial change to layer things correctly, and we've tried to do best efforts there, but yes, there's still cases where it's not the case. And if you have a way to layer it well, then it's great. Otherwise, yeah, for now, unfortunately, we have to keep it that way.
Okay, thank you. Yeah, anyone else? Ian, I see you unmuted. Did you have any comment?
No, sorry, that's my mistake.
Okay, so there's this CPU discussion. Ettore, I don't know if you are part of it, but do you mind giving an update around like the third-party CPU backend meetings that are happening?
So I wasn't directly involved into that meeting, but I know my manager Arek talked to Phil. That's my understanding. So essentially, we do have a public-facing machine now that we can run CI. And there was also some discussion on, my understanding is that several companies, including AMD, NVIDIA, and others, would be interested into collaborating to try to create a proof of concept for a CPU backend for, is yet to decide what kind of CPU to work on, or maybe multiple CPUs. And I believe AREG is going to schedule a follow-up meeting with everybody interested. And he posted the meeting plans on the Slack, in one of the Slack
Yeah,
channels.
it's in the third party Slack channel. Yeah.
So
if anyone here
people
is
interested can just
Yeah.
let him know by responding to that message, and then we'll organize a meeting and decide, what do we want to do, who want to participate, how do we want to do it. Things to discuss is whether we should do the development directly in Tree, or we should do it in a different branch that in which case whether it should be a branch in the OpenAI repository for this work, or should be completely a separate project. So there's a bunch of logistics to discuss, and we'll essentially, I think at that meeting we'll discuss about a few of those things and get people ideas of what they are interested in. If they have any idea for like initial design, they'll be welcome.
Yes, Thomas, go ahead.
Yeah, I was actually curious about that. I'm guessing. I wonder what your thought is. It sounds like this CPU backend design pitched, I think, by Phil, and like for others to jump on, most likely would be significantly different than what you have at Intel, because you're going through the POV path, right?
Yes, absolutely. I mean, I don't even think that. I mean, I think probably so, but actually, there is a little bit of misunderstanding. The current fork that we have of Triton, we are not generating SPIR-V directly. We're actually generating LLVM-IR. And then we translate LLVM-IR to SPIR-V using a Chronos tool to get to because our backend, the language for the backend is not LLVM-IR, is SPIR-V. So we have to translate it, but we are actually just generating LLVM-IR plus built-in functions plus annotations to help us out. So it's much more common. The design is now much more close to both what AMD and you guys NVIDIA, and for what's done for NVIDIA, right? In terms of CPU support, I would think that we would want to lower to LLVM-IR, not SPIR-V. But it depends from different. It's everything is on the table at this point.
Of course. Okay.
There's also a CPU backend in the Triton shared project that lowers thermal IR, and it supports x86 64 as well, and the writing ARM support as well. So it's not performant, but correctness wise, it works.
Mm-hmm.
So may I ask, what's the main driver adding CPU support? Is it like just for kind of functionality checking, or so like I'm missing context entirely here?
I think there is a need for, at least there is some people that need to be able to write CPU kernels efficient, and ideally like being able to write in the same language for CPU and GPU kernels is actually very beneficial.
And if you get good performance, it could even be interesting to PyTorch, because PyTorch right now uses Triton to offload to GPU, but it may then, if we have a Triton backend that generates CPU code for several CPU and is performant, then they may actually want to adopt it. And I think that right now they lower to OpenMP code. So, you would have to actually parallelize some of these operators in Triton using either the OpenMP dialect, which is now, much more functional in MLIR than used to be. Like last I looked at it, like maybe over a year ago, there was OpenMP 3.1 support. It may even have well, I guess we don't need OpenMP 4.5 because that's just gonna be for offloading to GPU. So,
Okay,
and Triton is already doing that very well.
Yeah, makes sense. Thanks.
So that could be interesting also for PyTorch to consolidate the ecosystem there.
Okay. Any other comments, questions? Okay. If not, thank you, everyone. We will post the minutes and the recording soon. Thank you. Bye.
Thank you. Bye-bye.
Thanks.